In this video, we're going to continue our discussion on second-order linear homogeneous differential equations. However, we're going to focus on the special case where we have constant coefficients. That is, p of x and q of x are constant and not a function of x. The general form for this differential equation is given by equation 1. And what we will see is that this ODE can be solved in a very systematic way. As with the other second-order linear differential equations that we have seen, equation 1 will have two linearly independent solutions, y1 and y2, leading to the general solution c1y1 plus c2y2. Now I want you to pause and think for a second. What form might y take? Observe equation 1. What we are doing is adding the solution function y and its derivatives after multiplying them by some constants, and all of that yields 0. So what can you conclude here? We can conclude that the solution function and its derivatives must differ at most by a constant multiple only. The only function whose derivatives are a constant multiple of itself is the exponential function. So we can propose that y would be of the form e to the mx. So let's evaluate the first and second derivative. So we have m e to the mx, and y double prime is m squared e to the mx. Now if we substitute these into the ODE, so that's into equation 1, what do we find? We have our constant coefficient a multiplied by m squared e to the mx plus our constant coefficient b multiplied by m e to the mx plus the constant coefficient c multiplied by our proposed solution e to the mx, all of this being equal to 0. If we factor out the e to the mx terms, what do we have? We have e to the mx is factored or multiplied by am squared plus bm plus c. And all of this must be equal to 0. Now this term here, e to the mx, can never be 0. Therefore, we must conclude that these terms here in the brackets must be equal 0. And this is what we call the characteristic equation. So before we go any further, let's just recap what we've done. We have a second order ODE with constant coefficients, and we notice that the only solution that could plausibly fit this ODE is of the form e to the mx, where m is still unknown at this point. So substituting this and its derivatives into equation 1 gives us equation 2 over here, which we note that the bracketed terms must be equal to 0. This term in brackets is called the characteristic equation, which is a second-degree polynomial with two roots, m1 and m2. And again, you can determine m1 and m2 using your quadratic equation. b squared minus 4ac divided by 2a. Now the nature of the solution will depend on the solution of the characteristic equation. So What I mean is that M1 and M2 can take several forms. They can be real and distinct. They can be equal to each other. Or 3, they can be complex. That is when b squared minus 4ac is less than 0. And in what follows, we will look at the 3 above cases and what the ODE solution looks like. So let's look at the first case. That is, we have real and unequal roots. That is, M1 is not equal to M2. And this occurs when b squared minus 4ac is greater than 0. So then the two solutions will be of the form y1 will be equal to e to the m1x, and y2 will be of the form e to the m2x. And you can check that these are linearly independent solutions. This gives us the general solution of y is equal to c1 e to the m1x plus c2 e to the m2x. The second case we investigate is that of real and equal roots. This occurs when b squared minus 4ac is equal to 0 in our quadratic equation. What this will give us is that m1 is equal to m2, and that will be equal to minus b over 2a. This gives us a first solution of the form e to the negative b over 2a multiplied by x. However, recall that we need two linearly independent solutions. How do we go about that? What we can do is apply the method of reduction of order, given that we already have one known solution to the ODE. We therefore seek a solution of the form y2 is equal to vy1. Before we carry out the reduction of order, we must transform our ODE into standard form. Recall that the result that we derived for reduction of order depends on the ODE being in standard form. So what we need to do is express the ODE as y double prime plus b over a y prime plus c over a multiplied by y, and this is equal to 0. Reduction of order tells us that this term v is equal to the integral of 1 over y1 squared multiplied by e to the negative p of x dx, where y1 will be equal to e to the negative b over 2a multiplied by x, and p of x will be this term over here. I will let you carry this out on your own, and I'll give you the final answer right here, where we find that v of x is actually equal to x. So this tells us that y2 is equal to v multiplied by y1, and that is equal to x e to the negative b over 2a x. This can be expressed slightly differently by saying that y of x, our general solution, is equal to c1 e to the mx plus c2 multiplied by our factor v, which is x, and then e to the mx, which can be simplified into this form over here with the exponential term factor out. The third and final case we will look at is the case where we obtain complex roots. This occurs when b squared minus 4ac is less than 0 in our characteristic equation. This leads us to two roots, where the first one is something called alpha, which is the real part, plus I beta, and the second root, m2, is equal to alpha minus I beta. The solution looks like y1 is equal to e to the m1x, which will be equal to e to the alpha plus I beta multiplied by x. And from our laws of exponents, we can separate this as e to the alpha x multiplied by e to the I beta x. Similarly, for y2, it will be equal to e to the m2x, which will reduce to e to the alpha x multiplied by e to the negative I beta x. Therefore, the general solution will look like y is equal to a, which is some constant, e to the alpha x, e to the I beta x, plus b, another constant, multiplied by e to the alpha x, e to the negative I beta x. Now, to try to put this in a form that we can understand, why don't we take advantage of Euler's identity, which tells us that e to the plus or minus ix is equal to cosine of x plus or minus I sine of x. This allows us to state that a, e to the I beta x, plus b, e to the negative I beta x, which comes from this equation over here, can be expanded as a multiplied by cosine of beta x plus I sine of beta x plus our constant b multiplied by cosine of beta x minus I sine of beta x. Now, finding the common cosine terms and grouping the common sine terms, we have a plus b multiplied by the cosine of beta x plus I a minus b multiplied by the sine of beta x, which allows us to say that we just have some constant c1, because a plus b are both constants. So c1 cosine of beta x plus c2 sine of beta x, which gives us the general solution. Y of x is equal to, so recall what we've done is that we've factored out the exponential term here and here, giving us e to the alpha x multiplied by c1 cosine of beta x plus c2 sine of beta x. In the next few videos, we will see what these three solutions look like and what they suggest about the system's behavior.